We'll start our discussions on reinforcement learning for the general state space setting. So what have we learned so far? We have S, A of S, alpha, discount factor, the function, so cost function C, which is a function of S and A, and then we have transition function S, A, W, and then we have noise distribution. N WTW. The thing is, I'm not using the stochastic kernel for the rest of the semester because it seems to me that many people are having difficulty understanding the stochastic kernel. So I'm just going to use the state transition function and the distribution function of the noise, knowing very well that everything that I'm going to talk about, if you go to the original references, they are all written in terms of stochastic kernel. Okay, so stochastic kernel typically is represented by P of ds prime given SA. But I know many people are not comfortable with this notation, so I'm going to use the state transition function and the noise distribution. Okay. But whatever references I'll talk about, they are all using this particular notation in their paper. So you have to be comfortable with it at some point of time if you wanted to read the original papers. So, in reinforcement learning, as is the case, you have generally speaking, you have three unknowns in reinforcement learning. You don't know the cost function, you don't know the transition function, you don't know the noise distribution. Okay, those are the three possibilities. Generally speaking, across all reinforcement learning papers, the state space is well known, action space is well known, state dependent action sets are well known, and discount factor is something that you pick depending on your choice. Okay. However, I will make a comment that in modern problems, whatever modern problem you want to look at, it's actually not clear what the state and action space should be and what the state dependent action set should be. So if you're working on a physical systems, it's quite likely, like physical system as in robotics or a vehicle, it's quite likely that you know what the state and action set and state dependent action set should be. If you're working on using reinforcement learning for battery pack optimization, it's not very clear what the state is going to be. And because some of those states would depend on what sensors you have to measure those states. Now, if you don't have the sensors and you call something a state, you cannot measure it, then you are again in the POMDP setting, and we are not discussing POMDP in this class. If you are working on creating new materials using reinforcement learning, it's actually not very clear to me what the state and action set there should be. I've read a few papers and I feel that the state and action spaces are very elementary, and that makes the problem way more difficult. So frankly speaking, I don't know in modern applications, which is drug design, materials discovery, battery pack optimization and things like that, I really don't know what the state and action space should be. And if you call something a state, whether you have a sensor to measure that state or not. Okay, so with that caveat, I'm going to assume that moving forward, these are the things that we are given, and the state action and state dependent action sets, these are all known, and this is something that you determine based on your own understanding of the problem statement. What we have done so far is we talked about this value iteration algorithm in the previous class. V0 equals to 0, Vk plus 1 equals to Tvk, and T of V is given by and this expectation is with respect to W, the noise W. We talked about in the previous class, we said that under certain assumptions, implies that V, K are LSC and inf compact. I mean, inf compact functions are LSCs, but I'm just writing it clearly so that we know that we are working with lower semi-continuous functions. And in some cases, if you add further assumptions, imply that Vk is Lipschitz or monotone. I didn't have time to cover other situations also, but you can also prove that Vk's are convex functions or things like that, monotone convex functions and so on. There are even further assumptions where you can prove that mu k's have some desirable properties or mu star has desirable properties, but we didn't talk about any of those situations in the class. The problem that really I find with the literature is that it's not written in one place, so it's scattered all over the place. And so collecting all of that information under the single umbrella requires quite a bit of effort that nobody has taken so far in the general state setting. Okay, any questions on what we did in the previous class before we proceed with today's class? Okay, awesome. So remember that when we were talking about reinforcement learning in the previous, for the finite state, finite action setting, we had introduced this notion of Q function. So we'll do something similar. So we have this Bellman operator. I'm going to introduce another operator. So I'm going to call it TQ of let me use small q to denote the function. This is C of SA plus alpha expected value of minimum A prime in FSAW This is the Bellman operator for Q update, and then I have T mu of V, which is a function of S, which is C of S mu S. Okay, so there are these two new operators that I'm going to talk about. We have talked about these operators even in the context of finite state RL. So I'm just updating those definitions for general state setting, but it's the same idea, nothing different. And if mu is a stochastic policy, then you have to do some sort of averaging here, right? So I know all of you are aware of how to do the averaging. Yes.
Sorry, I guess before, did you write the mu in terms of the q, or has it always been p?
This one. This is the Bellman operator for Q function. This is the operator for evaluating the policy mu. So this action is taken according to the policy mu, and the action here is taken according to the policy mu. Yeah. So in the actor critic setting, we want to evaluate the policy mu, so we need to apply this particular operator repeatedly in order to be able to compute what the value function of mu looks like. Okay, any questions on this? We had exactly the same operators for finite state setting as well, except that in those cases, the state and action were all finite sets. This was finite set, this was finite set, and so on. So everything was easier to understand. In general, when you are doing this sort of minimization for continuous state, continuous action setting, you get into a lot of measurability issues. But as we defined under these assumptions, there are no measurability issues that you have to face because everything is very well defined and easy to work with. Okay, any questions so far? No. Okay, wonderful. So before I proceed to the general state RL problems, I want to do some thought experiments. Okay. The thought experiment is around evaluating this Bellman operator at every point of time. So remember, we have to apply these algorithms on a computer. And I have to be able to store a lower semi-continuous functions on the computer. Okay. So what I'm going to do is, I'm going to assume that I have an extremely powerful supercomputer. And I have an operator pi, I have a function class f. I'll make things a little bit clear, and I have a projection operator. Pi f. Okay, so for now, just assume that the projection operator is simple. I'll define this projection operator in a bit, but let me give you an example. Let's say my function class f is f from R to R such that f of t equals to summation ai sine omega I t. I equals 1 to n. Okay, ai is in R, omega I is in R. So that's my function class. I use n sinusoidal waves and I multiply it by some real coefficient, and that gives me my function f. I want to store this function on a computer. How would you store this function on a computer? What's the easiest way to store this function on a computer? So remember, this function, technically speaking, maps the entire minus infinity to plus infinity to minus infinity to plus infinity. Okay, so it's a very complicated function. And arguably, you can list out, you can create T1, T2, T3, T4, all the way up to T infinity. You can evaluate the function and you can store it as an array on a computer, right? But is that the best way to represent this function on a computer? What's a better way to represent this function on a computer?
Maybe storing the amplitude and the frequency.
Wonderful. So you can store the amplitude and the frequency. So let me say that I'm going to do pi of f of a function f as a dictionary, and then I can say, I can save an array like this, and I can have I can store this, right? That's much easier to store on a computer. Yes?
That's not a projection operator.
It's not quite a projection operator yet, but I'll make it a projection operator in some time. But I'm just trying to do this thought experiment where I have a very complicated function. I'm able to put it on a supercomputer in a very compact way. Okay, I can do that at this point of time. So there is a complicated function space. For each function, I'm able to represent that function on a supercomputer in a very compact manner. Okay, same thing, I can have the function class f from R to R, and I'm going to write ft as summation I equals 1 to n ai t raised to n, t raised to I. If this is my function class, once again, I can just store the a1 to an in my array, and that would be able to represent this function class. So in some sense, what I'm doing is I have a function, that function is complicated. I'm trying to replace it with a simpler representation without really changing the function. At this point of time, I'm not changing the function. Very soon, I'll be changing the function. Okay? Is this concept clear? So let's say I have a supercomputer, and in that supercomputer, I can apply this operator pi f, and I can store a lower semi-continuous function on that supercomputer. Okay. So my function class now is the set of all lower semi-continuous functions from S to R. And my projection operator right now is extremely complicated. I'm running it on a supercomputer, and I'm able to represent any lower semi-continuous function in the computer using this operator pi f. And I'm going to run the following iteration. So I'm going to pick f0 equals to 0, and I'm going to pick pi f composition t fk. I'm going to call this fk plus 1. So tfk gives me a function. It's a lower semi-continuous function. I need to store it in a computer. So I'm going to use this pi f operator to come up with a representation of that function that I can store in the computer. I'm going to call it fk plus 1, and I'm going to run this iteration over and over again as k goes to infinity. Let's try to understand what happens in this particular setting. So let's say I want to determine what is fk plus 1 minus v star, infinity norm. Anyone remember? So in the homework assignment 2, you had proved something about the Bellman operator. What was the Bellman operator? What did you prove from assignment 2? TV1 minus TV2 less than equal to, anyone remembers? Right, everyone remembers this is something we had proved in assignment 2. Okay, so I think we had also proved this in the class, but I do recall that you guys have all solved this assignment 2, so this is something you have proved. I want to come up with I want to figure out what this error bound looks like. Okay, so what is this equal to? This is pi f composition t fk minus v star infinity norm, which is less than equal to pi f. Okay, so what is pi f doing? Pi f is not really changing the function at all. So I can just write it as t of fk minus f star, and because v star is a fixed point, I can just write it as v star equals to tv star. This is less than fk minus v star under the infinity norm. Yes?
Sorry, Sorry, why did you remove? Why could you remove the projection?
This one?
Yeah.
Because my projection is not really changing the function itself. It's just changing the representation of the function. So instead of writing it as a polynomial, I'm just storing it in terms of the coefficients on the computer. Right? So pi f of f is the f itself. I'm not changing. So pi f is just a way to store that particular function, but it's not really changing the function itself.
I don't know. To me, it's really strange because it seems like what you're describing is a parameterization, not a projection. You're saying like we have a function class, we can parameterize it using a finite number of parameters.
I don't still want to go to the finite number of parameters. There is,
okay,
yeah,
but, you can somehow represent it.
I can somehow represent that function.
The notion of projection is really very different. It's a way of actually getting those parameters from a function.
That's right.
Outside.
Exactly.
The class.
Exactly.
And
so we'll get to that in a bit.
So if we just start out by saying T is always inside the class.
Right.
But it's not clear why we even need to talk about it.
Because in a few minutes, I'm going to make this function class f somewhat restricted, and I'm going to project it, but I'm not still going to do any approximation. So when you say finite parameter, then there is a lot of complexity that comes in. So I don't want to still go to the finite parameterization yet. I want to go step by step. Okay. So this is just changing the representation of the function. It's not really changing the function itself. So pi f of f is still the same as the function f. And so I can write this as t of fk. V star is a fixed point, so I can write it as t of v star. I know that t is a contraction operator with respect to infinity norm. So I can write it as in this particular manner. And what that gives me is the fact that limit k goes to infinity, fk is actually equal to v star. So if I have this powerful supercomputer and I can represent any lower semi-continuous function on that powerful supercomputer, and if I apply this particular algorithm, in the limit, I'm going to get v star. Okay, I'm going to get a representation of v star on that particular supercomputer. Any questions so far on this?
So I guess we could have done all this without the projection.
We could have done all this. We did that without the projection in the previous class. Okay. Okay, wonderful. So all of us understand this. Now I'm going to make the change, and I'm going to make this projection operator a bit more concrete. No questions on this? Okay. So if I have a powerful function class, I'm able to converge to the optimal solution in the limit by applying the same value iteration algorithm with a projection operation. Now let's make the function class f somewhat restricted. So, and I'm going to define pi f of h as minimum f h minus f. F is in capital F. So my h could be a lower semi-continuous function, but f could be the class of all continuous functions. Okay, so I start with a lower semi-continuous function. I keep getting lower semi-continuous function at every point of time. I don't have a powerful supercomputer. I have less powerful supercomputer that can only represent continuous functions. And now I am going to have to project this lower semi-continuous functions onto a continuous function set, and then that's going to be my projection operation. Okay. Sorry? What is the norm here? Very good question. Depending on the book you pick, there are very different loss functions that you use in order to do this projection. So we'll talk about it again in some time. Right now, let's just assume that it is infinity norm, even though nobody does projection in infinity norm. Okay. Okay. Let's apply the same algorithm now. My f0 is equal to 0. My fk plus 1 equals to pi f composition t fk. But remember, by the way, I will still mention nobody can do this projection. Not even a powerful supercomputer can do this projection, but we are doing thought experiment right now. So let's assume all of this can be done. What happens to this algorithm? What does this converge to? And how far is it from V star? V star is where we want to be eventually. That's what my optimal value function looks like. And this Bellman operator converges to V star, which is where I want to be. But now I have a less powerful supercomputer, and therefore I need to figure out what the error between V star and this fk is going to look like. So let's try to analyze this function. This is equal to projection pi f composition t fk minus V star infinity. I'm going to use triangle inequality, and I get pi f composition t fk minus t fk plus t fk minus t V star. What is this equal to? So this is a non-zero error. So I have a lower semi-continuous function here. I'm representing it by a continuous function now. So I'm going to get a non-trivial error here, just because I'm not using the right function class to represent my function. This one is very good because this is less than equal to f alpha times fk minus V star. So this is the error. So this one is can be bounded by some function by the distance between fk and V star. This one is going to be inherent in this particular operation, and therefore it is called inherent Bellman error, and it is defined as follows. I'm going to call it IBE, which is a function of the function approximating class f, function of t of f. I'm going to define what t of f is. It's a function of infinity, and this is supremum over all f in f, infimum over all g in f, or maybe I'll call it f prime because I need g in some time. F prime minus Tf infinity, and T of f is just a Bellman operator applied to the function f for all the functions in the function class script f. So the inherent Bellman error depends on the Bellman operator, depends on the norm that you are picking, depends on the function class that you are picking. Okay, any questions so far? Yes.
It seems like when you define the IDE,
Right.
you use the function t. You didn't use t of f. T of f is like some extra thing.
So T of f is used here. Yeah.
The t is just that. T is an operator. Right? You use the operator t.
I have used the operator T, yeah.
But then you defined a new thing, which is t of script.
No, T of f, this is used here.
Right, but
This one is T of f.
t of little f.
This is the entire, so you have the little f from the function space f, you apply the operator t, you get a new function, and you're collecting all of that function and calling it T of f. Okay. So for instance, you start with the continuous and bounded functions, you apply the Bellman operator, you get a lower semi-continuous function. So now this T of f contains lower semi-continuous function, because once you apply the Bellman operator over a continuous function, you end up getting a lower semi-continuous. You could get a continuous function, but you could get a lower semi-continuous function. So T of f could be very, very much bigger than the function class f itself that you started with.
Right, but let's say that I know that that middle argument is just the set of lower semi-continuous functions. Right, this middle argument of
That's right. That's right.
That's not a. Now I don't know enough to actually implement this because I don't know what the t operator is anymore.
So right now we know what the, I mean, why do you not know the T operator?
Because you haven't given it to the IDE. You're saying IDE knows three things. It knows f, it knows these two sets, and the norm. But my point is it actually needs to know the operator.
Oh, I see what you're saying. Okay. Okay, so the way they define it is, so I understand what your point is. Your point is that you can say, if I erase this particular part,
Yeah.
then the operator T is going as an input here at this point of time, and then, right. But actually the way the literature has defined it is they put T of f here, and, but yeah, I mean, this one will also work as a definition. But that's not how most of the papers write it. They write it as T of f. Okay. This concept was defined in this particular paper, Munoz and Shepeshwari, 2008, for the first time. I think the title of the paper is Finite Time Bounds for Fitted Value Iteration, and that's where they define this inherent Bellman error of the function class f. Okay, and as I mentioned, inherent Bellman error depends on the function class, the Bellman operator, and the norm that you are picking. You can pick different norms for projection, and you can use different norm for identifying what this particular norm should look like. Now, as I mentioned, a lot of this work, this body of work has not been well investigated. So the theory is somewhat incomplete in my mind, because the way you do the projection and the way you find this particular error could be completely different, right? And so therefore, people have not done a careful study of this particular area. So at this point of time, I'm just going to assume infinity norm here and infinity norm here, but you could potentially have L2 norm here, and you can pick infinity norm here, or you can have L2 norm here, and you can have L2 norm here, and so on and so forth. So you can pick whatever two different norms you want in order to define the Bellman error and in order to do the projection. Okay. But for now, let's just assume that it's infinity norm, and you can change the norm here with whatever is your favorite norm. There will be some problems, some theoretical problems with this in terms of convergence guarantee. But for now, let's just work with infinity norm because it's easier to understand. And I don't have to introduce a lot more other notations under infinity norm. Okay, so one thing that I want you to think about, you have this error process, fk plus 1 minus v star. This is the error process. This error is less than equal to alpha times the error at the previous time step plus some error, inherent Bellman error that gets added, right? So this inherent Bellman error is an upper bound on this particular error that you're seeing here. So what would this error process converge to? Or what, I mean, this error process may not converge, but there will be some bound that you can get on the eventual error. So can someone work on it and tell me what that eventual error is going to look like? Okay, so let me call this error at k equals to fk minus v star. I have error at time k plus 1 is less than equal to inherent Bellman error plus alpha times error at time k, which is less than equal to inherent Bellman error plus alpha times inherent Bellman error plus alpha square times error at time k minus 1. And I can keep doing this upper bounding. And what do I get? Error at infinity is going to be less than equal to inherent Bellman error over 1 minus alpha. What could be another problem with this sort of approach? So as you are moving along in the space, so let me draw a picture. So this is my, let's say, the set of measurable functions. What I have mentioned earlier is measurable functions is extremely large. It contains all the continuous function, limits of continuous functions, and also discontinuous functions, well-defined discontinuous functions. I picked a function class. This is my function class f. I pick a point f within this function class f. I apply the Bellman operator T of f. Then I project it here. This is my phi f composition T of f. Here is my V star. And I have this complicated function space in which I am doing this projection. One of the risks that you have is this particular thing will not necessarily converge. Okay, so this fk plus 1 need not necessarily converge to some eventual limit. But whatever the error is, that error would always be bounded by the inherent Bellman error of the function approximating class divided by 1 minus alpha. So if you are running a reinforcement learning problem, this is not reinforcement learning yet. We are still in the deterministic operation situation. Not deterministic, but we know everything right now. And you are running this value iteration algorithm, or rather, this would be called a fitted value iteration problem. If you're doing that, you may not have a convergent sequence. If you don't have a convergent sequence, how would you troubleshoot? What would you do if you don't have a convergent sequence? Why would you not have a convergent sequence? So typically, if you're doing something like this and you don't have a convergent sequence, it's quite likely that the inherent Bellman error is very large for the function approximating class that you have picked. So one of the assignment problems in the current assignment, assignment 4 that you have, I ask you to solve a dynamic programming problem, and you start with the state space. You take the function approximating class as a linear function of the state, and you will find that the error accumulation is very high at every point of time. On the other hand, if you expand the set of functions to s and log of s in that specific example, you will see that it converges to the optimal solution in a certain number of iterations. Okay, so you have to pick a very careful, you have to be very careful with what function approximating class f you pick, okay, so as to make sure that this particular iteration converges. And in the example that I have given you in the assignment, the inherent Bellman error becomes 0 by just changing, by adding one more term to the function approximating class. But that's a carefully constructed example, so it's not going to happen all the time. But what I meant to say is you have to think very carefully about the function approximating class that you're picking in order to solve your problem in a general state space setting. It's not the case in finite state space because everything is represented by a matrix or a vector, but in infinite state space, you almost always have to fit the function to some function class, and that creates a lot of problems in convergence in real world. Yes?
Just to understand, so you said that even if it doesn't converge, we still
the error would still be, yeah.
So that means it could be in some limit cycle.
Yeah, it could be in some limit cycle,
So
yeah.
why is, maybe we don't care? I mean, if my error is good enough,
yeah, then you are fine, right? So that's what I'm saying. If IB is very small, even if you're not limiting, you're still very close to the optimal solution. So let's say you're looking at limit fk minus v star, and this is less than 0.001. That's good enough, right? Because your inherent Bellman error of the function approximating class is very good. Another thing that you might recall from your assignment 1, the value iteration, you had run some value iteration and you had plotted at what point of time the policy changes. And what you would notice in that particular curve, I mean, almost everyone got that question right. Even if the value function is far away from the optimal solution, your policy is still optimal. So you don't have to be at V star in order to get mu star. You can be close to V star and you can still have a very good policy, almost near optimal policy. So that's what this idea is, that if your Fk is close to V star, you will have a good enough policy for real world application. And the only thing that matters is how rich your function approximating class is and what the inherent Bellman error of your function approximating class is for that specific problem. Yes?
Is that because your action space is discrete?
In that particular example, it was because the action space was discrete.
Because if action space is continuous, like in investment, then market is still have some average.
Very small error. If the error is of the order of 0.001, would you even call it an error, right? Because you're not going all the way to infinity anyways to compute the optimal solution, right? Yes, please.
Because the inside the norm, we are they are functions now, so we can imagine it as infinite long vectors.
That's right. That's right. That's exactly right. Okay. Anything else? Okay. I have one more picture that I want you to keep in mind because I think it's very important to have these pictures. So I have f of s. This is s. This is a continuous function. I apply this operator t. I get t of f of s. and I might get something like this. This is f and t of s. So this is still lower semi-continuous. This is LSC. But this one is continuous. And now you are approximating this particular function with a continuous function. Let's say the function that you come up with would be something like this. This is a continuous function. This is your, let's say, phi t of f. And this distance is your inherent Bellman error. Well, you are taking supremum over all such functions, but this gives you an idea of what the inherent Bellman error is going to look like if you keep approximating this t of f with the functions in function class pi of f, then you get some error, and these errors will keep accumulating, and that's going to derail your optimization. It could derail if your function approximating class is not picked carefully enough. Now, this is the concept that I have introduced in the context of value iteration algorithm. So this is fitted value iteration algorithm. You can do essentially the same thing with Q learning, with the Q iteration as well as with the policy function. So let me just introduce the same thing, even though I would admit that the notion of inherent Bellman error has not been extended to the Q function space or to the policy evaluation type of problems. But I think you can, not sure why you would be interested in extending that concept, but you can definitely do it in some paper that you might be writing in the future. So let me just extend that concept here. Okay, so in the case of fitted value iteration, your f is a set of functions from S to R, and it might have some properties. So let me write it as a subset, because I want to keep it open. You could do this fitting f. So what all things have you done so far? You have used transformers, you have used neural network, you have used k nearest neighbors in your assignment. So those are the three functions. And you have also used XGBoost, which is a discontinuous function approximator. So your function approximating classes could be very different, and you have used 4 in your assignments already. Okay, and there are many more that you can study in different books. And there you have pi f composition t. This is the operator that you apply at every time. So this is the fitted Bellman operator. This is not a standard terminology. I'm using these terminologies to make it clear in the class, but if you use something like this in your papers, make sure that you define it appropriately as we have defined it in this in the lecture. Then you can have fitted Q iteration. I'm going to use the function class G, which is a function G from graph of A to R. Once again, your function class G could be neural network, transformers. Nowadays, transformers is the rage in Silicon Valley. So if you look at robotics, people are building foundation models for robotics, and they are using transformers as the function approximating class for robotic applications. And you can have the same definition. Let me use this. Composition TQ. This is the fitted Q I have to, and then you will have the fitted policy evaluation, and there again we'll use the function f, and you will use pi f composition T mu. So you will evaluate, you will pick a function f from this class that you have defined. You will apply this T mu operator, then you will project it back. In each of these cases, you will have inherent Bellman error, and those Bellman errors will accumulate, and you will get some sort of error bounds eventually as time progresses. Any questions so far? So if you are solving a problem and you see that your function class is not adequate, what would you do? So use the two-layer neural network. So this is again something that you have done in your assignment, so I would love to hear what your thoughts are. But you have a two-layer neural network, you try to fit a function, you have huge error, what are you going to do? More layers? Okay. So you can, somebody can do more layers, what else can you do? Just change the function approximating class itself. So you were using neural networks, use convolutional neural networks. You were using CNN, change it to transformers. You were using transformers, you can change it to decision trees or regression trees, right? So it really depends from one application to another, how many discontinuities it has, whether or not it has discontinuities, whether the value function is going to be Lipschitz. If you know that the value function is going to be Lipschitz, you can use neural networks to approximate it. If you have discontinuities in your function, as was the case in assignment 1, when you were fitting 2x mod 1 function, you saw, I mean, almost everyone saw that decision trees was able to approximate that function much, much better than neural networks, or I think transformers were also able to approximate it very well. But neural network was particularly bad in terms of approximating that discontinuous function. So all of you have seen it in your assignment, and the reason why that assignment was given is for this particular class, actually. Yes?
So here we're talking about approximating the value function or Q iteration.
Yes.
We also have to approximate mu, right? Make an implementable
That's right.
policy itself.
That's right.
And
Oh,
so
yeah, very good point. Yeah.
are you going to talk about that separately or explicitly, or just we're going to just say mu is some parameterizable normal function?
Yeah, so the question there is, what the question was that when we are talking about this inherent Bellman error, what about mu? Because mu is also something that we need to approximate. The problem is that the theory of approximation for mu is very, very scant. Like, I have not seen many papers on how do you approximate mu in a better manner and what kind of guarantees you get in terms of being able to solve this value iteration algorithm if you have to store mu in some fashion. So the general tendency in the reinforcement learning literature is to just focus on the value function, especially in the general state setting, because it's much easier to work with the value function or the Q function. Working with mu in the general state space setting is extremely difficult, but I do have some thoughts on it. So remember, when we talked about the value iteration algorithm and we talked about value functions being lower semi-continuous, value functions being Lipschitz, and value functions being monotone, we didn't actually talk about what exactly mu star or mu t looks like, mu k looks like. it turns out that mu k also might have some structure, but it requires additional assumptions on the state transition kernel and the cost function, something that we didn't talk about. However, generally speaking, in general state space setting, it's very difficult to satisfy that mu star would be Lipschitz function. Okay, it might be discontinuous, so mu star might have a bunch of discontinuities. So let me again draw that, because that's so if you look at inventory type problems, you have S, you have mu of S, and you could have something like this could be your mu star. This could be what your policy looks like. If you look at all the papers that has come out from DeepMind, they are using the same neural network for representing the value function and for representing the policy, the same neural network. So what they do is, I'm assuming that everybody is familiar with neural network architecture because you have implemented it in assignment. But what they tend to do is, you have the state S, you have a whole bunch of layers, and then you will have one output, which is the V of S, and you will have other output, which is mu of S. But this is a probability distribution over the action set. So this is actually outputting the probability distribution over the action set. So so you have the same network all the way until the final layer, and in the final layer you give some output as the value function, and the rest of the output is the policy. So they tend to share the same neural network until the final layer. So this is what the current. So many of the state-of-the-art performance that you have seen in neural network, in reinforcement learning or deep reinforcement learning, tends to use this particular architecture. What that means is they have imposed the restriction of Lipschitz policy. Okay, they have imposed that restriction by virtue of picking the same neural network. However, the actual policy could be discontinuous. So then again, you are approximating this discontinuous policy by some sort of continuous function, okay, by virtue of picking that specific architecture. Yeah.
What was your intention behind the different unlabeled nodes here? Like what's the meaning?
So this node, for instance, is giving you what's the probability of mu star S equals to A1.
But this would be for a discrete action space?
This is for the discrete actions. So almost everyone discretizes the action space. If you talk about all the latest DeepMind work and many other work, they are all discretizing the action space. So if you have a motor that gives us output 0 to 1, or rather that's the action space A for a motor, they are going to replace it with 0.01, 0.02, 0.99, and 1. And then they are going to do it on discretized.
I feel like these things, to me, are the most important things. Like, you can have all this theory.
Right.
And there's like a few people in the world that just do the theory.
That's right.
Like, to me, I think what's more important is what's happening and how students can use this.
Right.
And
right.
so like these things are incredibly important.
Right.
So I don't know, just kind of like an offhanded comment that like, oh yeah, this is how it's done. Like, to me, that I would like the course to have a lot more of this.
Lot more of this. So remember when I mentioned that I assume that the action space is, if it has a metric, it's a general action space. So now you could have an action space which is 0, 1, or you could have an action space which is discretized version of 0, 1. But as long as you assume that the two actions are close to each other and these two actions are far apart from each other, you are still within the general action space setting. Okay. Yes.
Is there a reason why people discretize it instead of use the general space?
Good question. So there is an informal argument, which is that in computers you can only write discrete numbers anyways, so discretizing it makes sense. That's the basic argument. I'm not quite sure what would be a better argument than that. It could be that I don't know. I don't have a good answer to that. Maybe if you discretize the action set, you get a policy, and that policy does well in real world, people are happy with it, right?
So
Yeah.
let's say I'm controlling a robot.
Yes,
And so I have like many different joints.
That's right.
And things.
that's right.
And if each one is discretized with a grid,
Yes,
I have this cursive dimensionality issue
Yes.
where there's no way that I can actually implement this network. Because, right, like the number of discrete actions I have
correct.
is way too big. So I'm a little doubtful that this is what's actually being implemented.
You are right, and what they are doing right now for robot is to use a diffusion model to generate the action. So that's a completely separate topic, and I don't want to get into that. But this is how they have done for many robots. But the kind of robots that you are talking about, which has like multiple joints, maybe 100-dimensional, 100 motors in the body, and so on and so forth, the reinforcement learning for those kind of robots have started developing just now, like in the last 1 year or so. Prior to that, they were small robots with 5 actuators or 6 actuators, and they were doing reinforcement learning on those robots. And in those robots, you can do something like this. It still makes things very complicated, but you can still, with enough compute and with enough processing, you will be able to demonstrate some performance, and that's what people were doing 2015 to 2022. It's the large dimensional robots, the higher dimensional action set robots. Those are the things that is the current sort of state of the art that people are still developing. I think it's not there yet, but it will. It's something that's in development in Silicon Valley, and there are millions of dollars being poured into solving the problem using RL. I don't know if that's satisfactory, but that's what the current state of the situation is. Yes.
Okay, so first, the neural network, the first output of the neural is a value function.
Yes.
And then from the second to the last, it's the
Policy.
They
Yes.
used to do this with one neural network.
With one neural network.
Oh, so
So this could be very large neural network, and this could be very large number of perceptrons in each layer. So and then they use this the same output. Sorry, the last layer. Some of the output, no, all the outputs goes to the computation of mu star, and one of them will go to the computation of V. Okay.
So they are putting the neural actor and critic together.
They are putting the actor, and so I wouldn't say they are putting the actor and critic together, but they are sharing the bulk of the weights of the neural network. Only the final layer weights are different.
Okay, this is my first question. The second question is, I remember Silver write a paper, some
Deep deterministic policy gradient. Yeah.
But, so you said from 2000, and this paper, I think he published on 2014 or something.
Yes.
And
Yes.
then you said between 2015 and 2022, people are still using this discrete test.
Yes, because the hand wavy thing is that if they share the same network, then there is some sort of regularization that happens. As a result of which, you have much better performance at every point of time. But it's not been studied from a theoretical point of view, but from practice, what is known is you get so sharing the same network allows the thing to regularize automatically, the training automatically, and therefore it gives you very good performance.
Okay, so my second question, all the Silver developed the deterministic
Yes.
But people still are using this approximate stochastic.
Yes. Yes. See, because over time there is different sets of groups and they have developed their own understanding of how this training happens for the specific problem that they are looking at, right? And so this particular thing, once it was known, everybody tried it, it kind of works, and so therefore everybody is using it. But if you ask me for what the theoretical analysis is, there is no theoretical analysis for these kind of systems. Okay. Yeah. Yes.
I feel like an alternative. So the way that you define the capital F function, where you have the stochastic input W,
right?
You could do the same thing in a network where you have the state come in, and then you have this externally generated like Gaussian noise come in.
Yes.
And then what the network does is it, basically colors or it processes the noise in such a way that a single node gives you the distribution, and then you don't have to discretize it.
The reason why I am using this noise W is because people here are not familiar with stochastic kernel, but the way most of the literature thinks of it is in terms of stochastic kernel. And so the way most of the literature treats it is S prime is distributed according to P bs prime given SA. And so they just generate this new state based on the current state action pair, which they plug it into a simulator and then they get the next state output.
But I think like you can always, I'm not might be wrong, but I thought you could almost always.
No, you are absolutely right. Yes.
With the deterministic F and the stochastic.
Yes, but you are absolutely right. Mathematically, there exists an F and there exists a W for which you can do this. Right. Practically, people are not willing to write that out. However, if you talk about it from a robotics perspective, you can actually write down the robotics dynamics.
I guess that's what diffusion does in a certain sense, because it starts with, this random state, and then you can do a deterministic diffusion if you want.
That's right.
And then it actually implements that.
That's right. Yeah. Yeah. Diffusion definitely does that. See, I think the key problem here is that depending on the situations, people have done very different theoretical analysis, which is what I'm presenting. I'm trying to combine all of the different notations and different theoretical analysis into a single sort of framework. So there is definitely some amount of information lost in that particular process. So compression always loses information, right? So I'm losing a lot of information in that process, but hopefully the thing that I really want to equip you with is if things are going right, there is no problem. If things are going wrong, you should be able to troubleshoot it and you should be able to pinpoint this is the reason why this particular thing is not working. Okay, and the whole point of this lecture and the subsequent lectures is for you to be able to pinpoint this is the problem. This is the reason why we are not able to fit the neural network very well, or why we are able to get such large errors in our estimates, and what can I do to fix those errors, right? So in some situations, let's say your policies are discontinuous, you are forcing the policy to be continuous like this. You will see a lot of errors when you are computing, when you are doing the value iteration, when you are running the value iteration algorithm. And if you see a lot of errors, you should recognize that maybe your policies are discontinuous, and therefore to use XGBoost to approximate the policy rather than use neural network to approximate the policy. Okay, so that's just the point I was trying to make. Any other question? Okay. Okay. So so far, I remember that when I had introduced this function projection, I had said that you have a function h, you're projecting it onto this function space f, and you minimize the norm, and then you hopefully get a function f that minimizes that norm, and that's your projection. In reality, we cannot really do function projection in that manner because I cannot really take two functions and compute what the norm between the function is, but I can approximate the norm, right? So now I'm going to give you a sampled version of these operators, which is exactly what we use in practice. So let's look into that. Okay. So let me write the two operators. So pi f of h is equal to minimum f in f, h minus f. I'm again, this could be any norm. It could be infinity. It could be L2. And then I have P of V of S equals to min E of S. Okay, so I can replace this this computation by the following. I have so you generate according to a distribution P, and then I have T hat V S. So Wi is of course the distribution of Wi is n, and same thing you can do for T hat Q. These are known as empirical Bellman operators. Okay, so there are two ways to, there are many ways, I mean not many ways, but this is the generally acceptable way for evaluating these operators. So these operators are very difficult because you have to do it at every state, and you have to do this function projection in a general, under a general metric, as we have mentioned here, right? So this needs to be computed at every state, and I have potentially countable or uncountable number of states. This needs to be done under this particular norm, and that norm is very complicated to evaluate, let alone doing a function optimization. So what do? We generate SIs according to some distribution phi. We have a loss function L. It could be quadratic loss. It could be cross entropy loss, depending on the situation. And then you do the sample average approximation of the loss function, find the best fitting function f. This is exactly the approach you have taken in all your assignment problems so far, whenever you were doing function fitting. So you picked some bunch of states and you had a function h that you wanted to fit, and you picked a neural network or a k nearest neighbor or whatever your favorite function approximating class was, and then you did this particular projection. Now this, I'm denoting it by pi hat, knowing well that this pi hat depends also on n. So the more samples you have, the better approximation you will have. So in the future, I'm going to make pi hat as a function of n, because I'll have different sample complexity for different samples that I'm using for evaluating pi hat, and different number of samples n that I'm using for evaluating t hat. But again, t hat here is also a function of n, how many samples I'm using to replace this expected value with respect to w with the empirical sum of the value function evaluated at the next state with these noises wi. And the same thing can be done for the q iteration as well, the empirical q operator as well, wherein you remember that this action A prime is the action set of f, the next state evaluated at wi, and this one is the next state evaluated at wi, and this one is A prime. And I'm doing this minimization of the q value and then taking the empirical sum and adding the cost function, and that gives me t hat. So what you end up doing when you are doing the implementation is you pick a loss function for your function approximation, you use the empirical operator, and the nice thing is when you compose these two operators, pi f hat composition t hat, you only have to evaluate these operators as SI. Remember that this h essentially is this particular value, t hat of v. So what you do is you evaluate this particular operation, you solve this particular problem at SI, right? So SI is where you're solving this particular problem, and then you get this value of h of SI, and then you replace that value here, and then you do this function fitting. So so at every point of time, you evaluate these operators at whatever SIs that you have generated. You evaluate these operators, you get these values, you plug this value in, and you do the function fitting in order to get your next iterate. And then you have this iteration fk plus 1 equals to pi hat f t hat fk. There's another complexity here, and depending on the paper you read, they'll consider different situation. So you can have the same set of SIs generated for all pi hat evaluation throughout the iteration, and you can have the same wi generated for the entire set of iterations. So these t hat and pi hat could be the same across time, or t hat or pi hat can be new across time. So by new across time means you are regenerating these SIs and these wi at every iteration in order to evaluate this pi hat and t hat. So again, there are two variants in the literature, same t hat, same pi hat across time. Study the convergence of this iterates fk, and resample t hat and resample pi hat at every iteration, and study the convergence of this iterate fk. Okay. Now the question that I'll leave you thinking about is why should this particular iteration work? Why should we imitate? So remember, this function is this operator is extremely complicated. I'm evaluating the Bellman operator and I'm doing function projection. Now I'm doing the empirical evaluation of Bellman operator. In fact, I'm doing it only at a certain number of points, and then I'm doing function fitting, why should this fk be a good approximation of vk, which is the original value function that we computed at iterates k? So this is fk plus 1. I have vk plus 1 equals tvk. Let's assume that f0 equals to v0 equals to 0. So I started with 0 function. How far are these two iterates? And more importantly, how far is fk plus 1 from v star? Okay. So think about it. Why should this operator be close to this operator? And if it is close to this operator at every point of time, does that mean that fk plus 1 is going to be, fk eventually will get close to v star or not? Okay, so I'll let you think about it and then we'll discuss it on Tuesday. Okay, thank you.